And so let's see. Okay, this is not important. Can kill it. Okay, so we we stopped on example with curve space, two-dimensional curve space, which is a surface of the sphere. Okay, so and I gave you home task to obtain all Christoffel symbols to show you. Yes, I forget to share my screen. Okay. Now. Okay. So now you can see my screen, I hope. Okay, do you see screen?
Yeah, we see.
Yes. Yeah.
Okay, fine. So I received some PDFs from you with the calculation of Christoffel symbols. And now you will help me to finalize and to see how we can obtain scalar curvature and the component of Riemann tensor. So, okay, we start, because on the previous lectures, we obtained the new objects which are Ricci tensor and scalar curvature, and let's train a little bit before we will continue with other things. So, okay, now I can see that we start to calculate one component of Riemann tensor, curvature tensor. So, as I hope you found the component of Christoffel symbols for such a kind of metric, which you can see here. And if we will take into account that some of the component of the Christoffel symbols are 0, so we will have only two summoned like this. And what we need to know, so we need to know the Christoffel symbols gamma 2 to 1. The same, we can write it instead to put the indexes, the numbers, we can put letters which represent which exactly coordinates we are using. So since we
Sorry, I have one question. If I understand correctly, we can do this homework for Friday, yes or not?
Yes, for 1 week I asked for Monday, but at least this is Friday. So I will wait up to Friday for this task to obtain all components of Christoffel symbols. And after this is task closed. So please don't send me later. Okay?
Thank you.
Okay, the same I can write like a phi theta. So this is just a point to to put indexes, and sometimes it's more convenient. So, and tell me please which is a solution some of you obtain for this component.
Minus cosinus theta, sinus theta.
Minus sinus theta, sinus theta.
Yeah, cosinus.
Cosinus. Okay, it's right. And also we will need gamma 1, which is, as we understand, since Christoffel symbols is symmetric relative to
I'm so sorry, where we get minus?
Yes, we have a minus.
However, we obtain it from term with minus as G22, comma 1. And this derivative is minus sine theta cosine. Sorry.
You have a
Yes,
question
yes.
about this minus?
No. That's
It's understandable.
yes.
Okay. So for the second one, please tell me the final result for this one. Gamma 1, 2, 2.
Cotangent theta.
Cotangent theta, right. So after this, so if we will continue this procedure, okay, so we can continue to obtain, I will put it to remind what we want to obtain, this one, this component. So, and we just need to write that this is d by, so x1 d theta from minus sinus theta cosinus theta minus, and so this is 2, 2, so this is minus, it will be this plus sinus theta cosinus theta, and on cotangents theta. So what we will obtain from this one, from the first summand, it will be sinus squared theta minus cosinus squared theta. Okay. And here we will have plus cosinus squared theta. So finally we will have sinus squared theta. So this is one of the component of curvature tensor. So, and this is, we understand, this is mixed. So with this curvature tensor has a contravariant and covariant components. So if we would like to find, and we would like to find, because you will see that finally when we construct the scalar curvature, we will need this one. So if I want to obtain totally covariant component, for example, this one. So what I need to do, I need to write corresponding to the rule of lowering or rising indexes. Sorry, I can put 1k, for example, rk 2, 1, 2. So the k is summation index. So it means that the non-zero component, it will be j11 r1 212 plus g22 r 2. I can you can check it at home, but this component, if we check it, this is equal 0. So finally we will have only this one component. And if we will calculate it, j11, this is r square, multiply on sinus squared theta. So this we found all one of the component of the Riemann tensor, which is totally covariant. Now let's find, in principle it's understandable that we need to find all components, of course. R2, 2, 2, 2, 4 times 2, 4 times 1, all combinations. But now I will try to do it much more shortly way, otherwise we need to spend a lecture for this. So a lot of components will be 0. This is the point, and why we have 0 component. of curvature tensor, this is, as you maybe can understand, this is due to symmetry of the metric which we choose. So now let's find tensor, Ricci tensor. And Ricci tensor, so the component of the Ricci tensor, for example, I want to find R22. So I remember that to find to find Ricci tensor, I can do this by swapping of the curvature tensor, but there is a restrict rule. It means that I can make a swapping of the indexes on the first and the third indexes. Okay, so it means, for example, for now I can use here, I can use mixed Riemann tensor 2I2. So you can see that I put a summation index and I have a swapping, so the same summation index I. This is first, which is contravariant, and the third, which is covariant. Okay, so for example, I can do this I after this below I22. So this is no permission. So and I need to honestly to write everything. So it's summation. It's 1, 2, 1, 2 plus R 2, 2, 2, 2. Again, you can check it at home, but this equals 0. And if you will write the expression for Riemann tensor, you can immediately see that this is 0 because you will have a derivative such ways, a derivative, for example, by theta, but expression under a derivative, this function depends on phi, like this. So, and again, we have, so we can see that if we will put here, this one, R1, 2, 1, 2. So this is sinus squared theta. So let's find R11. And I will find it a different way. So just also represent how we can do it. Another way I can do like this. So I can make a swapping. For example, this I did because I used mixed component, mixed representation of curvature tensor. Now let's consider that I have totally covariant Riemann tensor. Okay, 1. And I need to apply metric tensor. So again, as you can see, I keep this rule which we obtained before with a swapping of the first and the third index. So this is property of curvature tensor and Ricci tensor which we obtained before. Okay, so I need to write that this is, I need to use all I and K for two-dimensional space. I have 2 possibilities. This is, and I will put, of course, only diagonal elements because I know that only this one non-zero. 1, 1, 1, 1. Okay, plus J 2, 2, 2, 1, 2, 1. So again, you can prove that this component of Riemann tensor equals 0. So non-zero, this is only, like this. So also what I have the component 1, 2, 1, 2. Okay. So, and here I have 2, 1, 2, 1. We remember that the Riemann tensor is symmetrical relative to, it's asymmetrical if we change. So let's look on this property. So you can see here, I will put it some like this. Here, the tensor Riemann are symmetrical when we have a permutation inside of the pair. Okay, so it means that to obtain this one with this order of indexes, I need 2 times to change inside one pair and the second pair these indexes. If I will change 2 times, it means minus on minus give me plus. So I will write finally that it's equal 1, 2, 1, 2. So now I'll remember that if I will, what is contravariant component of the metric tensor with 2, 2, okay? So covariant this one, and contravariant, as we know, due to the fact that the combination, the product of 2 metric tensor contravariant, this is unit tensor. So G to 2 equal 1 divide r squared sinus squared theta. And we multiply on sinus squared theta, which we obtained before. So we have r squared sinus squared, okay. So we obtain 1. Okay. So we obtain all non-zero components of Ricci tensor. This is Ricci tensor for this case. And so non-zero component. Others are 0. 1, 2 is 0. And now I want to find, should be 0. I want to find, but it doesn't matter because when you will find now scalar curvature. So what we, right. So scalar curvature, it means that we need to make a swapping. And finally to obtain the scalar value, which doesn't have any indexes. So if I have covariant components, covariant representation of Ricci tensor, let's put it ik. So I need to do like this, okay? So this I and k, this is summation index. Taking into account, and now you will understand why I don't care about component of Ricci tensor with not equal each other indexes. So because I understand that in this summation, of course, I need to put I equal 1, k equal 2, so and not obviously the same. But I know that metric tensor is not 0. Components of the metric tensors are not 0, only for diagonal elements. So it will survive only G11 and correspondingly R11 plus J22, R22. Others, if I will even write J12 and I will find R12, it's by definition will be 0 because we have a metric which is which has only diagonal elements, non-zero. So and
I'm sorry, however, why we can do in expression in second expression. So we already calculated only curvature tensor for case where we have 1 as upper index and 2, 1, 2 is lower indexes, and that's equal to r squared sine theta squared. Okay,
yes, this one. Yes, this one.
Yes.
Mm-hmm.
Sorry, only sine squared. So why we can just replace or we just multiplied it by G.
Why we obtain this one? Yes, we multiply on G11. So this give us R
G11, where 1 is lower indexes. Yes?
yes, lower indexes and
okay.
lower indexes, yes. I will write here just to, because G11 equal R square, G22 equal R square sinus square theta. But if we, due to the fact, let's write, I know here, for example, that G, for example, I, K on G, K, P equal delta I P, which is again 1 I equal P, 0 I not equal P. So from this we obtain that J I K. I can note in this, it's not, for example, G11 contravariant equal 1 divided on G11 covariant. So because it's expressed through the unit tensor. Okay, this understandable.
Yes, okay.
So, but here, yes, but here we put just this is exactly, this is G11. So, okay, so finally, we just need to put here exactly G11 contravariant, which is now will equal 1 divided on R square. This is G11. R11 unity plus, and here J22 1 divided R square sinus square theta multiply on sorry, R, it's not without R. So because this is this one. Oops. So, and this disappear. And finally we have 2 divided on R square. So finally we obtained that the scalar curvature is equal to divide on R square. Yeah, now I remind you remember that I said that I don't remember. So it's with accuracy of 2, the Gaussian and scalar curvature different from each other. Now I remember that Gaussian curvature, which can called the letter K, equal 1 divided on R square. So scalar curvature, so this is Gaussian. There is such a kind of object as a Gaussian curvature. And maybe you met it in analytical geometry when you discover the surfaces like this. So, but what is important, and now we can write that Gaussian curvature, this is a scalar curvature divided on 2. So, this is scalar curvature. Let's put it for this kind of the surface. What we can see that scalar curvature is positive. And again, we discussed that, for example, for Gaussian curvature, which has a long principle, or much more precise, it's a long formula, but for a simple, some symmetrical surface, it can be considered as a K proportional to 1 divided R1, R2 for such a kind of surface. Since for the sphere R1 equal which R1 and R2, this is the main radii of the surface. So for this surface, the main radii are the same, R1 equal R2 and equal R, because we organize, we can create this surface with one radius. which you can see from metric 2. So, and this is for the sphere. So it will be 1 divided on r square. We also can see that, understand that if we consider r tend to infinity, in this case, r tend to 0. So, and we have limiting case, we have a flat space. So this is why, for example, with such much more simple representation, what I said now, so you can see that when we make this radius really huge, so it will mean that if you will choose such a part for us, it looks like flat part of the curve space. Okay, so the same as for with the Earth. Earth is a solid sphere, but for us the radius is huge within our feeling, and if you will look on horizon, it looks like a flat space. Or in a desert, it looks like a flat space. So, and in principle, we could make a decision that the space of the Earth is really flat, but because it looks like a flat, but it doesn't mean that the Earth is really flat, as we understand, because it's a solid sphere. And to understand that this is a solid sphere, this is so we can, due to the fact of when you sit on the beach looking on the sea, and suddenly you can see that ship go out from the horizon. So, and this is representation that in any case the Earth has a curvature. Of course, we also can, and I will give you home task, another kind of example, which is for us also interesting and important, because when we will speak about model of the universe and the different spaces of the universe, we will speak about positive and negative curvature and zero curvature. And let's consider the surface. This is saddle surface. In two-dimensional, this is saddle surface. In a much more general case, it's called Lobachevsky space. And how we wrote it? This, okay, the S square, which is the square of interval, which is the same as the square of the length, has a metric, has a following metric. So this is r square, the theta square plus r square sinus hyperbolic square theta the phi square. So this surface is different from the previous one, because I already spoke a little bit about this. The surface like a saddle, horse saddle, like this, and this organized the surface. So I can try to reconstruct it, show that this is surface. Okay, so and this surface are created by two radii. One radii, this is this one, R1. I mean in geometrical representation. Here we put the same radii, so we can consider that radii is the same. Okay, for this case. But in principle, to understand geometrically what is this, so this is R2. So it's already understandable that these radii are allocated on the different different side of the surface, the curvature for this case you need to obtain. I will put as a final result which you need to obtain. It will be the same 2 divided on r square, but with a minus. So, and in this case, the curvature is negative. Scalar curvature is negative. This is home task. Let's obtain it the same way which we did for positive curvature. Okay. So, okay, let's for this these examples. I will finish on these examples. Just want to say that, of course, it can be much more complicated. Surface now we consider the 2 kinds of the surfaces which has a constant curvature. It will be not a constant, maybe already said you. For example, for the torus, the curvature is can change the sign. So on this side, this part correspond r less 0, so this is negative curvature. In the inner side here, the surface, this is here positive curvature, and in these 2 points the curvature equals 0. So this is in this case, and in principle you have already you have enough knowledge to obtain this the curvature of the toroidal surface, which is depend on the angle, as we understand, on this angle theta. So it's depend on which. Yes.
I'm sorry. This home task is also to this Friday, or it's on next Friday?
This home task plus 1 week, so it's up to next Monday.
Thank you.
Yeah. So so and in this case the curvature depends on the angle. So this is one is, I would like to say that this is a more complicated surface and axisymmetrical. For 2-dimensional and 3-dimensional, it can be also the same things that it depends on the orientation. And just in advance, I would like to say that, and you will see that our world, by fortune for now, we consider the space in the universe, which is with a constant curvature. But we don't know exactly this like this or not. We will see and we will discuss that really the observational data tells that there is a conditions, isotropy and homogeneous of the distribution of matter, which tell us finally that the curvature of the space should be constant, positive, negative, or 0, but constant. But now there are discussions that maybe due to the fact that Hubble constant has a different value, which obtained by different methods. Sometimes discuss that maybe this suggestion can be not correct, and maybe universe is much more complicated. But this is under consideration. Now we will start to. Now we will consider. Let's kill it. Such a important expression, we will obtain it, we have time to do it, which in principle, this is important because this is the principles, finally we will obtain one part of the Einstein equation. This call the second Bianchi identity or differential Bianchi identity. I will write second. Okay, second. Bianchi identity. So what it means. By the way, okay, I have not a lot of time, so I will not put some philosophy or history. Okay, what we will, if we will have time, I will speak about this. So what I will use now, okay. So I will need the first Bianchi identity, okay, this one. So it means that if you have a covariant derivative of curvature tensor and we made correspondent permutations, cyclic permutation, this equals 0. And now I will use it. So I have R, J, M, K, L, covariant P, for example, okay? And after this, I made this cyclic permutation. R, J, I just rewrite what we obtained before. M, P, K, covariant L, plus R, J, M, P, oh, no, sorry, L, P, covariant K equals 0. So this I wrote the first Bianchi identity. You can refer to the expression which we obtained before. Now I'm doing the following. I will multiply this identity on metric tensor with indexes I and J. And I will also I will take into account that G, I, J, covariant derivative, for example, P, the covariant derivative of the metric tensor equals 0. This is also a property of metric tensor which we obtained before. It means that I can include, I can put metric tensor inside of the operation of covariant derivation. So it means that I can write this one, all this one like this. G, I, J, R, J, M, K, L, covariant P, plus G, I, J, P, K, covariant L, plus, and here also. Covariant, okay. So what I can see in the first summand, I can see that so it's just a line of the metric tensor, even not, and it means that the index, the one of the index will become contravariant. Okay, M, K, L, covariant P, plus here also R, I, M, P, K, covariant L, plus, and here I just make one index above, M, L, P, covariant K equals 0. Now I will make operation of swapping, but not, I will see, can I make this operation of swapping for some of the summand? I will put K equal 1. So I will consider this identity for the case when K equal 1. On what I will have. So in the first summand, it's exactly correspond to the swapping of the curvature tensor, which give us Ricci tensor, because this is swapping on the first and the third indexes. So it will be ML covariant P. Okay. I will put it so instead K now I put E, Instead K, I here put E. Okay, this one. Here I put E. You rewrite, but I will use much more short way. So I look on this sum, and what I can see that I need to change P and I. And in this case, I can make a swapping by first and the third indexes. It means that, look, I will explain. I can write this like I will make a permutation of the indexes, and permutation with two last indexes. It means that it will be minus. And after this, I can obtain to make this to create Ricci tensor MP covariant L. Okay. So I will clean it. You can, if you, so can I clean it? It's understandable.
Yeah, understandable.
Okay, so now I will write here minus R MP covariant L. About third one, so what I can do, I will write it like this. I can play with the indexes which are summation indexes. I now instead of I will put K M L P and here K. Doesn't matter. I call it K or I or what I want. Okay, this is summation indexes, so I can put any letters. But to be careful that this letter will be not one of these which are not summation indexes. So, and after this, I will apply twice the metric tensor, which is unity, so I can do it. Now I will look I will apply this metric tensor on this one, and this, and let's put another color. This indexes with these indexes. So what I will obtain from this one? Let's write it separately, not to repeat everything. I will have R. So I will, this index yellow, it will be below MLP, and this index K with covariant derivative will go above. Okay, and I also make permutation of the indexes here. It will be RM with minus I, LP, covariant I. Why I'm doing all of this, you will understand a little bit later. So I try to simplify this expression as much as possible. So, and I play with the indexes corresponding to the rule which I have to obtain a more simple expression. If I can do it, but we will see that really we can do it. So now I will rewrite everything ML covariant P minus R M P covariant L minus minus R M I L P covariant I equals 0. So now I want again to make a swapping and to reach a much more simple element. This is scalar curvature. So I will multiply on GML because I can see that in this case I have RML. Let's see what it will be. Again, since the fact that the covariant derivative of the metric tensor is 0, we can write, I will write more sorry, more in detail, sorry. So, ML, RML, covariant P, minus GML, RMP, covariant L, minus GML, RMI, LP, covariant I, equal 0. Okay, let's see here. So we obtain just a scalar curvature. So this gives us R covariant P. The second summand gives us R, which is became the tensor which became mixed tensor. So it will be L M P. Sorry, because again here we have M and here M summation index. Covariant L. And here minus, look, it's exactly swapping by the first and the third index. So we will obtain richer tensor. R, IP, covariant I equals 0. You can see that it's already became more simple, but the problem that we have a different derivative here. Here a P, here L, and here I, and even contravariant. I would like to express all of this, if it's possible, inside one derivative. So let's try to do it. And the first summand I can represent as a look as a delta unity tensor LP R covariant L. I can do it. For example, we can consider this is we can consider the case, for example, IP and some vector P I. Sorry. So what it will be? It will be delta 1 1 A1 plus delta 2 2 A2 plus what is not equal, the indexes which if they are not equal to each other, so it will be just a 0. Okay, so and we understand, and this equal 1 and this equal 1, so it will be equal just AP. This is just a simple proof why we can write like this. We didn't have a lot of time to consider all manipulations, so but this we can write. Oh, sorry, like this. Okay. The second summand I will leave because it's what I have here L covariant derivative L and here L, but with the third one I need to do something, and I will do this. So I again, instead of I will put index K, for example, the summation index. Doesn't matter because it's summation index. And I will apply twice KL, JKL. So Q. So equal 0. This K I will apply to this index, and this K I will apply to this index. Oh, it's better to put a different color. This K to this index. So one making rising of the index, another lowering. So what I will have, again, let me write delta P L R L I leave it like it is, as it is, RLP covariant L. And here I will have minus R. So I will make the index K with the covariant derivative, which is above, below. And the second index, otherwise I will be here, equals 0. So, and look, we have two the same summand, so we can write, and the same, which is important, derivative, this L, this L, and this L. So we will put it, we'll collect it in one derivation, so we can write delta PL R minus 2 RLP covariant derivative L equal 0. Is already everything what we want. If we will just, to write more convenient way, we can multiply this on GKP, and in this case, if we apply the metric tensor to each of the summand under parenthesis, we will have KL R minus 2 R KL covariant L equals 0. Due to the fact that again that delta LP, if we can this multiplying of two metric tensor give us the unit vector, unit tensor. So it means that GKL equal G for example, KP not delta multiplying the delta PL. So we used for the first summand this one. So this is final expression which we obtained. This is called the second Bianchi identity. So I already over the time. And the corresponding tensor, and what is important, just 1 minute and we will finalize. The tensor which we obtain, we really obtain the tensor because all values multiplier and summand which we have, they are tensors, and as a result we also have a tensor minus 2 RKL covariant L equal 0. We can write also this another way in a covariant form and multiply on the minus 2, which usually much more. So I can write like this. This is the same, so it's also right. And this tensor, which is tensor, because tensor reaches scalar curvature, metric tensor, so and covariant derivative creates the tensor finally, called even recall it, called Einstein tensor. Einstein tensor. So this is important object which we obtained. And we can see on the next lecture, I think that on the next lecture, we finally write Einstein equation. And second. So, and this expression is very important to obtain finally the Einstein equation for gravitational field. From the point of geometry, we have everything what we need. So it should be Einstein tensor. So finally, you can see this is tensor of the second rank, which we exactly need to construct the equation of gravitational field. For this lecture, it's all. I only want to say that Einstein spent a lot of time to obtain the equation of gravitational field, and he wrote in his letters to his friends that he spent that this is much more complicated than special relativity, and he also says that, and this is due to the fact that he didn't know this second Bianchi identity. So, and if he could know this, maybe he could find it much quickly that he did it. So, and this very famous phrase of Einstein's that he known mathematics not well because he didn't visit lectures of his professor very often, enough often. But of course, Einstein known mathematics very well because to use with the tensor analysis, especially for this time, it was really the new mathematics. But in any case, this expression, this identity, he didn't know. Identity, this is Einstein tensor, but identity, which I would like to. So this is identity of Bianchi identity, the second Bianchi identity. Do you have some questions?
Our home task is check that
Our home task to obtain all non-zero, if you want, Christoffel symbols, components of Riemann tensor, components of Ricci tensor, and finally the scalar curvature. Maybe
okay,
not
so-
again non-zero. What you everything what you need to find scalar curvature. Okay.
Okay.
So, do you have some other questions?
Yes, one question about maybe second Bianchi identity.
I need to make just a second. I need to make screenshot. Yeah, ask questions. I am listening.
Yes, so we start our
Sorry. I have a question. I don't know who this DDDDD. So if I don't understand the name, I will not take into account this because I
It's
can't.
bug of Zoom. It's not our mistake. Or it's not someone's name. It's a mistake of Zoom.
Okay. So thank you
Така
for explanation.
вже тиждень він точніше перейменовує рандомно людей, ось такі символи. І не знаю, чи ти будеш цього разу, чи хтось інший.
Strange. It's very strange. I see it maybe I didn't do attention before, but okay. So your question, please.
In proof for second Bianchi identity, we started with first Bianchi identity.
Yes.
And as I understand, we can use manipulations which we using to all these terms separately. And does it mean that RJMPK covariant derivative L plus and I'm sorry, and RJMLP, I'm sorry, second and third term is the same, just equal each other, or not?
Mm,
How is it works? So
you could see all procedure which we did. In principle, yeah. In principle, we can consider one summand, another summand. Yes, as you said, the second summand, the third summand separately. But you know, it's not a good point to consider. You know, it's better to do procedure step by step with all identity, and when you will see that you can do some, because for example here we multiply all summand here, for example, okay, not here, in another place, where here, for example, all identity on the metric tensor. So you need to keep it with the same indexes like this. So, but in principle, yes, maybe you are right in sense, if I understand correctly your question, that finally, yes, for example, this summand and this summand, they became equal if we will do this procedure which we did. But again, you remember, we did a swapping, we did some, yeah.
So, however, all procedures which we did do not change exactly what this tensor is. So we can, or for example, our third term in maybe in our second expression does not equal our third term in fourth expression.
I don't understand maybe correctly, but what we did, what's the main point of what we did? We considered the swapping of Bianchi, of the first Bianchi identity. So this is the main, if you would like to tell this by one word. But to make this swapping correctly, when we put, you know, the same indexes, you investigated, yes, that if you will do, yes, this, you obtain the two summand which are equal each other. So I'm not sure that I exactly give answer on your question, because I didn't understand maybe correctly. But so if you, the point that you can try to do it by different way. So this is one of the representation of the proving how to obtain Bianchi identity. It's maybe not once. So I for example, sometimes I did it with another way. But in any case, yes, from 3 summand, finally you obtain 2 summands. This is, yes, it's like this. So
Yes, so my point is, again, from this point, can we think that in first Bianchi identity, second and third term are equal? Or
no,
we need
no. In the first Bianchi identity, no. The second and the third summand are not equal each other.
However, after our operations,
Yes,
during this
yes. After
approval,
operation,
that
yes.
became equal.
Yes, because we made a swapping 2 times, and even you know, so finally when we did it, it's became the same. It's like you know, we obtained from a curvature tensors Ricci tensor. So and some, you know, combination of the Ricci tensor of the curvature tensor, it doesn't mean that the same combination of Ricci tensor we will obtain. So here not here these summand are different. But after all this operation which we did, so we obtain that finally we have this expression. yes, which to someone which became equal each other.
Okay, understood.
So if you don't have any questions, I will see you. We will see you on Friday, and on Friday we will obtain, as I hope, we will consider. We'll consider quickly stress energy tensor, or the same as called energy momentum tensor, which is the right part of the Einstein equation. After this, we will find expression for the metric. So we there are a few ways to obtain Einstein equation. I will use for now much more short way. So we will go the way from starting from Poisson equation, so from classical mechanics, and to generalize it for general relativity, for Einstein equation, for relativistic case. So, and as I hope in the next lecture we will obtain Einstein equation. After this, we quickly consider the effect of which we have due to this equation, including this problems with the time and like this. And after this, we will formulate the metric of our universe, and we solve Einstein equation for a metric of our world. So this is for plan for next few lectures. If you don't have a question, see you on Friday.
Goodbye.
Thanks for action. Goodbye.